Good day, dear ones. Uh, Welcome to Power Lab and welcome to ECE360 Power course. It's You will be dealing with the labs with me, and I'm Gannaya Bommali, your lab instructor. I think you know me. I'm assuming that you did ECE260 course here, uh, and you dealt with me and did the experiment on various machines like a DC machine, synchronous generator, uh, induction generator, induction motor, three-phase transformers, all kinds of stuff you did experiment. So this lab is the extension of 260. So you'll be again dealing with the machines here, in addition to the some simulations. Uh, but the focus is more on the power system related equipment. Basically the first equipment, first machine you will be dealing with in power system is synchronous generator. That is the power generating thing. So, and today you'll be learning how to synchronize. You studied the synchronous generator, how to modulate, what are the different characteristics, all kinds of stuff in EC260. So today, uh, this is the extension of that lab. So you'll be synchronizing this one with the grid, and then how to control the active and reactive power in the power system kind of thing you'll be learning here. Okay, so I'll just focus the camera to the lab manual and show the instructions, and then we'll go from there. So this is the lab manual here. So on synchronous machines, I use term synchronous machines because the synchronous machine, this machine can be used either the generator or motor depending upon the situation. So here the objectives are given here. The synchronous, the first objective is to synchronize the synchronous generator with the power grid, and then we'll try to control the active power by using the prime mover, and then control the reactive power using the exciter kind of thing. So these are the three objectives. The lab is very simple in nature, but it's very informative. If you are planning to work in the power generating station, anywhere like hydro power station or nuclear power station or thermal power station, so these concepts will be very useful there to understand the operation there. So hopefully you learn something out of it today. And this is the data template I will be using to record the values. These are the previous values. Either I would be overwriting or I will be using the same values if they are same while doing the experiment. Okay, so let us dive into the first step here. So generator synchronization is the first one. So the objective is to synchronize the synchronous generator with AC power grid, AC power network, or power, we call it grid basically. So we'll do initial setup here. So there are some few instructions there. So first one is on power supply settings we'll be doing. So make sure the power switch is in off position and the voltage control knob is at 0 position. As a safety requirement, we will be making sure this instruction first, and then we will be identifying the terminals which are required to use it in our circuit diagram somewhere here. If you see the circuit diagram here, so basically you'll be using the 1, 2, 3 terminals that of the power supply. So that's the AC fixed power supply, and we'll be using the variable DC power supply here, and we'll be using fixed DC power supply here. So that's why we would like to know on the power supply, these are the things we'll be noticing. That's why the instructions are given here. Where are they? Yeah, here. So 1, 2, 3 terminals on the power supply. These 3 terminals to be considered as a power grid for the sake of this experiment. Since we cannot since this is the experimental thing, so we have a small generator here. So we'll be using the fixed power supply as the power grid. But in reality, the power grid will be a big network kind of thing. Identify the fixed DC power supply and variable power supply terminals, and make sure the gray cable coming from DC and from the DAI is connected to the 24 volts low power supply. Locate the small red switch and turn it on. So let me execute this step, and then we'll go to the next step kind of thing. So this is the power supply. I think you are not able to see so this is the power supply here. Okay, and then we will be using this 1, 2, 3 terminals as a power grid, and then we will be using this variable DC power supply to drive the prime mover, and this fixed power DC power supply to power the exciter there. So that's why, so this one will not be using here. And then as a safety requirement, we should be keeping the voltage control knob at 0 position there, and then the voltage the power switches should be at 0 before we do any connections here. And one of the instructions mentioned about the gray cable here. So this gray cable, coming from the DAI is connected to the control power supply or not, we have to make sure. So it's already connected there. So just we'll be locating this red switch here, and when we turn on this switch, you can see that there is a green LED is there, it will turn on. So that means we are powering the DAI so that the DAI and the computer they will communicate kind of thing. So the next step is about coupling the timing belt. So open the front cover of the prime mover by pulling slightly 2 tabs. The timing belt should be in the slot below the prime mover, and get the timing belt out. And if you are here, this is the precautionary step it is given, because we found that sometimes the students fingers they get caught between the belt and the pulley. So that's why this step is given. But today I will be showing you. I'll be connecting myself, so no need to worry about that. And we'll couple the synchronous generator and the prime mover with it, and remember the timing belt should pass between the guiding rollers to ensure proper tension. So let me execute this step for you, and then we'll come back to the next instruction. So this is the synchronous generator motor module here, and this is the prime mover dynamometer. So if we open these tabs, then you can see that the timing belt is there. So that's this timing belt we will be coupling these two machines together. So this is the pulley here, and this is the pulley, and these are the guiding rollers. The belt should be in between these two, so that to create a proper tension. So you know how to connect the timing belt, I guess, because you did the previous course. But let me show you again how to connect. It's very simple. So I generally put the belt one side, one of the pulleys there, and I just hold on the other pulley. Put the belt on the other pulley, and at the same time I will turn it clockwise direction. It will go inside. Now you can see this is light little loose. If you leave it like this, what happens? The speed of this one and the speed of this one may not be same, because there is chance of slipping kind of thing. So now, to make sure both the speeds are the same, so we have to create a tension between in the belt. So what I do, the first one is easy. Just I put this one on top of the bottom roller, and the top roller I lift it with the fingers. At the same time, I pull down the timing belt, and at some point it will go inside. So once it's gone inside, so I just try to turn it and see if they are aligned properly or not. If there is misalignment, what will happen? The belt will come out. That way it is indication of its misalignment. And also you can also see these two frames, they are also matching. If you are physically here, you would see they are in line. I don't know whether you are able to see it with the camera or not, but their alignment also you can make sure with this alignment of the frames kind of. So once it is done, so just I will close it. So I'll just pull the tabs and then push it. It will go inside. You may hear click sound. So once I'm done, and I just I test it by pulling a little bit to see whether it's coming out or not by accident. Well, when we are doing the experiment, if it's coming out, then it is a difficult thing to manage. So that's why I try to test before. So this tab is not working. So at least this tab is working. So when I pull it, so it is not coming out. That's fine, I guess. Let me try. Yeah, it's not going. But anyway, so let me focus on the next step before wasting time here. So the next step is about prime mover settings. So the input terminals, as a prime mover input terminals, we have to identify so that we can use it in the circuit. And then we have a mode switch, because the prime mover can be used either generator and as either dynamometer or prime mover. So we need to identify the mode switch and set the mode switch to prime mover position. And then the display switch is there. This can display either speed or torque. So we'll we want to know the speed first. That's why we'll set the display switch to a speed position. And then this prime mover needs its own power supply to operate, because there is a big PCBs there in order to process the information, like converting the torque signal or voltage speed signal, all kinds of stuff. It has its own power PCB. So this PCB requires a DC power supply, or I think it's AC power supply, control power supply it requires. So that's why we'll be locating the control cable box, and then pick up the 24 volts power cable, a gray color cable I'll show in a moment, and then connect that cable between the data acquisition system and prime mover. So let me execute this step for you, and let me change the camera position. So this is the prime mover dynamometer module here, and then this module will be using it as a prime mover. So we need to know the terminals. This is the prime mover input, so because it's as a prime mover it needs electrical input, so that's why these two terminals will be using. So 1 and 2 terminals, these are the terminals will be using. And then this mode switch, we have to select put it in the prime mover position there. So this side is the prime mover position, and then this display switch, it can display either torque and speed, so we will be setting to speed. And then we would be needing some power supply here, and just this is the control cable box I just picked up from the top of the station there. So I open this, and then this is the cable. It's talking about a gray color cable here. So this cable, and I can just connect it between the DAI. So this is these are the two jacks. You can put one of the jacks there, and then the other thing I will just so you can see that I just adjusted the position to show you the jack here. The moment I connect here, you will see the green LED will be on. So power on, you can see that one that is on there. So right now it is set, since it is set to speed position, the LED here, there are 3 different things are there. So it's showing revolutions per minute, so that means it will show the speed in revolutions per minute kind of thing. So that is the step about this step. So we'll go to the next step. So the next step deals with the synchronous generator settings. So what we'll be doing, we'll be testing the windings. So the synchronous generator, so as always, I don't know whether you are familiar with my approach or not. I generally, before I use any equipment, I generally make sure my equipment is working or not, working properly or not. So the first and foremost thing is we are dealing with the windings. The windings, either they can be short or they can be open, based on the previous operations or some kind of things. So that's why we wanted to make sure the windings are properly working or not. So for that purpose, we've identified the starter windings. So like 1, 2 will form, terminal 1 and 4 will form one winding, 2 and 5 will form another winding, 3 and 6 will form another winding. So that's a 3-phase generator. That's why there are 6 terminals are there. Each winding will be having 2 terminals, starting and ending. And then identify the DMM and turn on, set the resistance function and select the lowest range, because we are expecting the windings to offer low resistance. Generally the resistance of the winding should be low, in order to avoid some like either copper losses or other losses kind of thing, or voltage drop kind of thing. So and then measure the resistance kind of thing. So okay, so then we will be taking some long red wire and black wire and measure the resistance and record in the template. So I will do that one, show you in a moment about that one, but just let's complete the things here, the instructions. So on identify the rotor winding. So we have basically in the synchronous machine, we have 2 parts. One is the starter part, has starter winding, and rotor part, which is rotating part, which has got rotor winding. So the rotor winding is basically, it's a field winding. The stator winding we also called as armature winding kind of thing. So identify the rotor winding terminals. 7 and 8 terminals are there, and this one has a switch to enable or disable the magnetic flux. So the switch is provided with the in series with the winding, so that we can either disconnect or connect the uh, power supply kind of thing. And then field winding, so there is an exciter control as also there to control the flux kind of thing. So on the DM, set the range to 2 kilo ohms and measure the resistance with minimum and maximum positions and record the values in the template. So let me do this one for you, and then we'll come back to these things, or maybe I'll just read this one. So basically this one deals with the recording the generator ratings. So at the bottom of the faceplate you will see motor ratings on the left side and the generator rating on the right hand side. So note both motor and generator ratings in the template, and you will see some ratings on the armature winding, note them as well. And then on the synchronous generator module, again there is an exciter switch. The switch should be in 0 position, and the exciter knob should be at 12 o'clock position kind of thing. So these steps will just execute and see what is going on kind of thing. So this is the synchronous motor generator module here, and that is the DMM we'll be using here. And on the synchronous generator, it was mentioned to identify the starter winding terminals. So 1 and 4 will form one winding, 2 and 5, 3 and 6. These are the 3 windings because of 3-phase power supply. And then we have a rotor winding here. So this is the rotor winding, and there is a switch here. So that switch we should be operating later, but for now we'll focus on finding the resistance of this starter winding then. Okay, so in the DMM here, so we need to identify the terminals we'll be using. So we'll be using the common terminal and the top red terminal, which can measure the voltage and resistance. So for resistance measurement, these two, top red and the black terminal we'll be using. And then we set the resistance function, kilo ohms function is there, but here this button is only the lowest range it can measure. It's 200 ohms it can measure it, and we'll turn on the power. So right now it's blinking because nothing is connected. It's just like an open circuit. Open circuit means infinite resistance. That's why it's not showing. When we connect the resistance, definitely that blinking will go away. We will see. So I have taken 2 wires, one long red and black wire kind of things, because it has to reach. Okay. So let me connect to one side and the other side. So it's better to use 2 colors when you're measuring the resistance, especially with current or voltage kind of thing. So this black terminal will go there, and if you see, this blinking will go away with the moment I connect the things there. So it is showing 11.97. So what was the previous reading there? 11 to 12.1. So I will just delete and 11.97 ohms. Control S. And the next one is next winding is 11.97. That's very good. So that means they are both are equal. So 11 0.97 again. And then next one is 11.99. It's very close, so the small difference we just neglect. So for a basically in a three-phase system, all the windings should be having the same offering same. So it's 9.98 it's changed, so I'll just change it to 9.98 there. So I'll save that one. And then the next instruction says identify the rotor terminals. This is the rotor terminals here, 7 and 8. So there is a switch here, and there are 4 poles are there. So the top one is the north pole, and there is south pole, north pole, south pole. Same winding going through all the poles, but in series. But the orientation is different, such that one would create north pole, the other would create south pole kind of thing, and alternatively it has that kind of thing. And then in series that winding we have an exciter. Basically it's a potentiometer to control the current there. So this one will control the current, means it can control the flux, and this one either to remove or give the flux instantaneously, like it's kind of a switch, on and off switch to enable or disable flux kind of thing, or current kind of thing. So that is the things about this one. And you can see here there is a motor ratings on the left hand side of the things, and the generator on the right hand side here, generator rating here. So basically the values would be same except the current rating. So it's 175. Our power rating is different also. So 175 watts it will give you as a motor. And then the speed should be this, that is the synchronous speed we call 1800 rpm. For both it's same thing, 208 volts. If it's a three-phase system, the voltage, if it's not mentioned anything, that voltage we treat it as a line voltage. So the phase voltage would be line voltage by root 3, that would be 120 volts, I guess, if you calculate. And as a motor it will take 0.8 amperes, but as a generator it will give 0.33 amperes. So it's a three-phase, sinusoidal symbol is there, that means it's three-phase, and 60 hertz frequency given there. So those things I think I already recorded from the previous experiment. So I just all these values I recorded there for you in the data sheet. And then on top of the armature the winding, there is also voltage mentioned there and current mentioned there. So this is the phase, so that's why if you divide 208 by root 3, it will give 120. So that is why this 120 is given the rating of the winding. That will give you phase voltage, but the current rating is 1 ampere there. So why there are 3 current ratings? One is as a motor is 0.8 amperes, as a generator 0.33 amperes, but the winding rating is 1 ampere kind of thing. So why they are different? So basically, if you are using as a generator, it can give 0.33, but if you are using as a motor, it will take 0.8 amperes to rotate it. That is the basic thing. In order to produce this much power, 175 watts power, so that is, I think, maybe because the power rating is 120 VA, if you convert, if the maximum power factor is 1, So if you convert into active power, it's 120 watts, and then this is 170 watts. That means the as a motor it is giving more power, mechanical power kind of thing. So that's why it's taking 0.8 amperes instead of 0.33. So when you design, so as a motor and generator, so you would be taking the highest value. So instead of 0.33, you will be designing the wire. The size of the wire should be withstanding 0.8 amperes. If it is able to withstand 0.8 amperes, then 0.33 is taken care, kind of thing. And now, so why is this 1 ampere instead of 0.8? So there is a safety factor for anything in engineering. So we consider a safety factor here. So in this, the lab1 guys, they considered as like I think around 0.8, 0.2 amperes more. So 0.8 by 0.2 by 0.8, I think around 25% something. More rating, over rating, the like safety factor than 1.25 times this value they created, kind of thing. So that is the reason of their different values. But the thing is, when we want to use as a motor, you will be focusing on this one, will not be focusing on those two. When we are using as a generator, we will be focusing on 0.33, will not be worrying about this one. When we are using individual winding, when we are testing, so we will be using 1 ampere kind of thing. So that's why there are three things there. So those things are recorded for you. So armature winding ratings are also 120 and 1 ampere there. And then the next step is to see it. Okay, so we'll be measuring the winding start rotor current, rotor winding also. So is that let me see, rotor, yeah, rotor field winding. Okay, so I will just use this one. So I'll just disconnect it, and then I'll put it in minimum position here, and then measure the resistance. So right now it is blinking, because that means the resistance may be exceeding the range there. So if I go to the next range, it is still blinking. Oh, that is strange. That means oh, this is off, that's the reason it's blinking. So now if I leave it there, it's showing 600 and something ohms. It's fluctuating because of, I think,